Assalamualaikum warahmatullahi wabarakatuh. Okay, for today's lesson, I want to do truss exercise analysis using stiffness method. Okay, I will choose one question from previous past year exam paper. Okay, I want to find the truss question. Not this one. This is flexibility. Not this one. Okay, this truss is for flexibility method. This is frame stiffness method. Stiffness method for truss. Okay, let's look at this question. This is a pin jointed plain truss. Okay, roller at support B and pin at support C and D as shown in the figure. Joint A was subjected to horizontal and vertical forces of 150 kN and 200 kN respectively. In addition, support D was displaced 15 mm towards the left direction. Using the stiffness matrix method, develop the structure stiffness matrix for the truss. And number 2, establish the force displacement relation. Force displacement relation. Okay, I want to choose this one. Okay, I just want to take the diagram only. Okay, this one. Okay, we go back to the note. Okay, we are going to analyze this truss. Okay, we will start with label this diagram. Okay, number 1, we have to label. Okay, we have to check. Okay, this truss has 4 nodes A, B, C and D. Okay, and the element number has also been given. Element 1 joining member C and D. Element 2, this is 1, this is 2, joining member A and member from node A to node C. Element number 3 joining B and D. Element 4 joining A and D, and element 5 joining A and B. Okay, so I need now I need to put the label for degree of freedom. Okay, by looking at this diagram, there are four four joint or four nodes, and there are three support. Okay, B is roller support, roller support. Okay, for D has pin support. Pin this one and this one, pin. Okay, and C also pin support, so like this. And I want to use different color for the unconstrained. Just now is constrained. Okay, so I use the green for unconstrained. So remember that each node must have 2 degrees of freedom. So like this. Okay, so for the green one is unconstrained, and for the red one is for constraint. Remember to start label from unconstrained. So I want to start label 1, 2, 3. Okay, finish the green first and then followed by the red. Okay, 3, 4, 5, 6, 7 and 8. Okay, and then the next one is I need to put the arrow. Okay, this direction and this direction, and this direction, and one more element is here. Okay, I can put any origin that I like, any direction that I like. Okay, next one I want to put the coordinate. Okay, so I will choose C as origin, so that the rest of the nodes will have all positive coordinates. So D. Okay, before we determine the coordinate for D, since the horizontal distance is not given, we have to determine first the distance. Okay, so this is 4 meter, 60. Okay, this is X. So by using trigonometry, okay, we will use tangent. Tangent 60 is equal to X divided by 4, and X is 4 tangent 60. Tangent 60 times 4. So the horizontal length is 6.93 meter. Okay, so horizontal length is 6.93 meter. The length. Okay, the length. Alright, so I will continue to label all the coordinates. Okay, so for D it is 6.93, 0. For A it is 0 and 4, and B it is 6.93 times 4, not times. Okay, so I have put all the coordinates. Okay, now I want to start. Okay, the most important thing in analyzing truss using stiffness method, we need to divide the structure into element. divide a structure into a series of finite discrete element. The keyword is element. Structure become element. Structure divide into element. Okay, the keyword is the structure divide into element. Okay, the truss here is a structure. Okay, in order to determine the structure stiffness matrix, we have to determine the element stiffness matrix first, and after that we combine the element stiffness matrices to get the structure stiffness matrix. So what we need to do now is we have to analyze element stiffness matrices one by one. So in this truss there are 5 elements. Element number 1. Okay, I want to extract one by one element so that you can see clearly, okay, and understand okay, the analysis. Okay, element 1. Okay, element number 1 is joining node C and node D. It is a horizontal element, and length for element number 1 is, the length is 6.93 meter. This is for element 1. Okay, I just want to draw back. Okay, joining C and D, so node C and node D, element is element number 1. Degree of freedom, okay, it is 5, 6, 7, 8. It is 5, 6, 7, 8. Okay, the coordinate is 0, 0 and 6.930. Okay, we start with determine the Cx and Cy, or lambda x and lambda y. Okay. Okay, so Cx and Cy. So for Cx, okay, okay, Cx we have to look at to the, so this is far, this is near, because arrow is like this. Okay, the arrow is always going to far. Okay, arrow shows the far end, going to far end, so it is 6.93 divided by 0 divided by 6.93, it is equal to 1. For Cy, okay, for horizontal member, Cy is equal to 0. Okay, so now I can get the element stiffness matrix. So for K1, okay, it is AE over L. Okay, AE over L, it is Cx square. Cx square means 1 square divided by L, divided by 6.93. So it is 0.144. Cx Cy 0, negative Cx square negative 0.144, 0. Then I get, okay, cx square, cy square 0, 0, 0, 0. Okay, I will get negative here. 144, 0, 0.144, 0, 0, 0, 0, 0. Okay. So this is the element stiffness matrix for element number 1. Okay, what most important is I need to label. Okay, I have to label from near to far. It is 5, 6, 7 and 8. 5, 6, 7 and 8. 5, 6, 7 and 8. So I am now finishing K1. Okay, I want to move to K2. Okay, K2 is a vertical member. The length is 4 meter. Okay, element number 2. Element 2, length is 4 meter. Okay, this is the element. Joining C and A. Joining C here and A here. Arrow like this. Okay, for the degree of freedom here and here. Okay, the coordinate as well. Coordinate here is 0, 0 and 0, 4. And for the degree of freedom, it is 5, 6, 1, 2. It is 5, 6, 1, 2. Okay, so again we will repeat the same process in order to determine or establish the element stiffness matrix. We need to have Cx and Cy first. So Cx, since vertical member, Cx is 0. Cy, it is 4 minus 0. Divide by 4, it is equal to 1. Okay, so from this we will calculate or establish K2. It is AE over L. Cx 0, Cx square 0, Cx Cy also 0. This is 0. And Cy square. Cy square means 1 square divided by 4. It is 0.25. So 0, 0, 0, negative 0.25. 0, 0. 0, negative 0.25. 0, 0, 0.25. Okay, so this is the stiffness matrix for element number 2. So what most important is the label. Okay, the label start from near. So it is 5, 5, 6, 1, 2. 5, 6, 1, 2. Okay. Okay, the next step is we will determine the stiffness, the element stiffness matrices for member 3, 4 and 5. Okay, for element number 3, element 3, since element 3, since it is also the vertical member, so Cx and Cy is equivalent to 0 and 1. So we will get K 3 like this. AE, don't forget to put AE. It is the same value. The same value. It is the same. Accept the label. Accept the label. The label is it is 7843. 7843. 7843. It is 7843. 7843. Okay, 7843, 7843. Okay, for element number, wait. Okay, let's say I just copy all this value here. Copy. And paste here. Okay, and for element number 4, the length is, element 4 is inclined member, so the length is it is 4 square plus 6.93 square root. It is 8 meter. 8 meter, so this is the member joining A and D. A and D. So coordinate A is 0, 4 and coordinate D is 6.930. The arrow is this direction. The arrow is this direction. Okay, CX, CY. For CX it is far minus near. Far minus near, it is 6.93 minus 0 divided by 8. It is equal to 6.93 divided by 8. It is 0.866. 0.866. And CY, it is 0 minus 4 divided by 8. It is negative 0.5. Okay, so for element number 4, K4, it is K4. Okay, it is CX square, 0.866 square divided by length is 8. It is 0.094. This is AE. Okay, CY 0.866. That's 6 times 0.5 divided by 8. It is 0.054. Okay, we calculate this value using the formula given in appendix. So it is negative 0.054. CY squared divided by 8. It is 0.031. 0.031. Okay, I may check the formula here. Okay, for for the, okay, this is the formula. Okay, cx square, cx cy, negative cx square, negative cx cy. Okay. Okay, we go back to this one. Okay, actually for truss, it is quite easy for the formula. Okay, it is 0.094, negative 0.054, negative 0.054, 0.031. So for the rest is just the same value but in opposite sign. Okay, so next value is negative 0.094, positive 0.054, positive 0.054, and negative 0.031. Again, the same value, negative 0.094, 0.054, 0.054, and negative 0.031. Okay, what most important is the label. Okay, we label from near to far. Near to far. It is 1, 2, 7, 8. It is 1, 1, 2, 7, 8. So this is 1, 2, 7, 8. 1, 2, 7, 8. Okay, this is for the element, number 4. Okay, for element number 5, K5. Okay, K5, element number 5 is actually similar with element number 1, so we don't need to calculate the value. We just have to copy back the value, but we label the new one. Okay, I just need to copy this, copy, and just paste here. Paste. Okay, so okay, and I need to label the degree of freedom for this is element 5. Element 5. Okay, element 5. Okay, look at the degree of freedom for element 5. It is from near to far, it is 1, 2, 4, 3. 1, 2, 4, 3. It is 1, 2, 4, 3 because we are referring to this one. We are referring to this. It is 1, 2, 4, 3. So it's 1, 2, 4, 3. 1, 2, 4, 3. Okay. Okay, now I want to combine all to determine to establish the structure stiffness matrix. I need to combine all. It is okay. Now we are determining the structure stiffness matrix for the truss. The symbol is capital K, and the structure stiffness matrix is equal to K1 plus K2 K2 okay, okay, plus K3 plus K4 plus K5. Okay, we have to combine all the element stiffness matrices in order to determine the structure stiffness matrix. And for the structure stiffness matrix, we since there are four nodes. There are four nodes. Since there are four nodes, okay, since there are four nodes, so we will get the matrix. The matrix is 8 by 8. 8 by 8. Because 4 times 2. Okay, and each node has 2 degrees of freedom. Okay, so we will establish the K. Okay, alright, we will establish the first value, which is 1 1. This is K. Okay, K. Okay, and K is equal to AE. Okay, don't forget to put AE. Okay, we better determine the element stiffness matrices and the structure stiffness matrix in terms of AE, because if we times the value with AE first, then we will find difficult to determine the too many numbers in the matrix. Okay, so let's remain AE first. Okay, AE. Okay, it is the matrix. Okay, I want to put the value here. Okay, for 1 1, 1 1 means we have to find where is 1 1 in all case, in all element stiffness matrices. Okay, 1 1, it is 0.144. 0.144 plus 1 1, 0.094 plus 1 1, there is no 1 1. 1 1 here is 0 plus 1 1 K1, no 1 1. Okay, it is 0.238. Okay, it is 0.238. It is 0.238. 0.238. Okay, next one is 1 2. 1 2, it is 1 2. 1 2 0. 1 2 negative 0.054. 1 2 1 and 2, 1 and 2 0. No, so the value is negative 0.054. It is negative 0.054. Okay, 1 3. Now we want to determine 1 3. 1 3. Okay, 1 3. Where is 1 3? 1 and 3 0. No 1 3. No 1 3. No 1 3. No 1 3. So the value, the next value is 0. The next value is 0. Okay, 1 4 1 4 1 4. Okay, find 1 4. Okay, find 1 4 1 4. It is negative 0.144. 1 4 1 4 1 4, no 1 4, no 1 4. It is only negative 0.014. Negative 0.144. Okay, so later I put the bracket. Okay, next one, 1 5 1 5 1 5. Okay, let's find where is 1 5. No 1 5, no 1 5, no 1 5. Okay, 1 5 here, 1 and 5, 1 and 5. 1 5 is 0, so here is 0. Here is 0. Okay, 1 5 1 6, no 1 6, no 1 6, no 1 6. Here 1 6, 1 6 is also 0. 1 6 is 0. Okay, 1 6 is 0. 1 6 is also 0. And 1 7, no 1 7. Okay, here 1 7, 1 7, 1 7. Negative 0.094, 1 7, no 1 7, no 1 7, no 1 7. Okay, it is negative 0.094. 1 1 1 2 1 3 1 4 1 5 1 6 1 7 1 8. Okay, we go to 1 8. 1 8 1 8, no 1 8. Okay, 1 8 here. 1 8, it is 0.054. It is 0.054. 1 8, no 1 8, no 1 8, no 1 8. It is 0.054. It is 0.054. Okay. Okay, this one. Okay. Okay, now we move to, okay, 2 1. 2 1 is negative 0.054. Okay, now I want to move to 2 2 because it is symmetry matrix, right? So we don't need to write in full matrix. Okay, the symmetrical value is enough. Okay, 2 2. So find 2 2. 2 2 0 here. 2 2 is 0.031. Find another 2 2. No 2 2. Here 2 2 is 0.25 plus 0.25, no more. So it is equal to it is 0.281. 0.281. Okay, 2 3. Okay, 2 3. What about 2 3? Okay, we find 2 3. 2 and 3. 2 and 3 0. 2 3 is 0. No 2 3. No 2 3. No 2 3. And no 2 3. So 2 3 is 0. 2 3 is 0. 2 3 is 0. 2 3 is 0. Okay, then we move to 2 4. 2 4. 2 4. Where is 2 4? 2 4. 2 4 here. 2 4 is 0. No 2 4. no 24, no 24, no 24. 24 is also 0. 24 is also 0. 0. Okay, 24 is also 0. Okay, 24 is also 0. 25, 25, no 25, no 25, no 25, here is 25. 25, 25, 25 is also 0. 25 is also 0. So continue. 25 is 0. Okay, 25 is 0. 26, 26, 26. Where's 26? No, 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 here. 26. 26, 26 is negative 0.025. 26 is negative 0.025. 26. Negative, it is negative 0.025. Okay, like this. 0.025. 27. Now 27, no 27, here is 27. 27, 27, 27, 27, 27, 0.054, 0.054, 0.054. It is 0.054, 27, 27 and 28. 28, no 28, here is 28. 28, 28, 2 and 8. Okay, 28 is negative 0.031, negative 0.031, negative 0.031 only. Negative 0.031. Okay. Okay, now we move to line number 3. We start with 3, 3 because 3, 1 and 3, 2 okay, has symmetry value. So we move to 3, 3, 3, 3. Okay, 3, 3. Find where is 3, 3. 3, 3, 3, 3. Here is 3, 3, 0. No 3, 3. 3, 3 is 0.025. 0.33. Where is 3, 3 just now? 3, 3, 3, 3, 0. 0.25. It is 0.25. Is 0.25. Zero point 0.25, 0.25, 3, 3, 3, 4, 3, 4, 3, 4, 3, 4, 3 and 4, 3 and 4, here is 3, 4, 0, 3, 4, 3, 4, 4, 3, 4, 3, 0, 4, 3, 0, no 3, 4. 3, 4, 0, 3, 4, 0. So it is 0. So it is 0 value. 3, 4, 3, 5, 3, 5, no 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 3, 5. It is 0. So 35 is also 0. 33, 34, 35. 36. 36. No 36. No 36. No 36. No 36. No 36. It is also 0. Okay, 37. 37. No 37. No 37. 37. Okay, here is 37. 3 and 7. 0. 37, 0. 37, no 37, no 37. So it is also 0. It is also 0. 37, 0. 38. 38, 38, 38. No 38, no 38. Okay, here is 38. 38 is negative 0. Negative 0.25. 38, no 38, no 38, negative 0.25. It is negative 0.25. Negative 0.25. So we need to do it like that continuously again and again until we get all the value, all the 8 times 8 value of structure stiffness matrix. Structure stiffness matrix. Okay, structure stiffness matrix. Okay, I don't want to finish this. Okay, I just want to put here is the bracket. Okay, the bracket. Okay, so the label here is 1, 2, 3, 4, 5, 6, 7, 8. And 1, 2, 3, 4, 5, 6, 7, 8. Okay. So this is actually KAE. Okay. Okay. So this is the structure stiffness matrix. I want you to continue until the end of this. Okay, why I want to stop here because actually whenever I establish this, I want to focus on unconstrained system only, and the boundary for unconstrained system is line number 3. This is the boundary. This is the boundary. This is the boundary. Okay. Okay, the boundary means this is unconstrained, so the rest is constrained. Why I want to focus on unconstrained? Because for unconstrained system, there are unknown displacement, and by having all the values for the stiffness matrix corresponding to unconstrained degree of freedom, actually I should be able to solve for the displacement. So corresponding to, okay, corresponding to unconstrained degree of freedom, or DOF, okay, I can actually write the equation, write the stiffness equation. Is as follow. Okay, this is corresponding to unconstrained degree of freedom. Okay, stiffness equation is as follow. It is Q is equal to KD. Q is equal to KD. The formula is Q equal to KD plus Q naught. Okay, what is Q? Q is nodal forces. Okay, what is K? K is structure stiffness matrix. What is D? D is the nodal displacement. Okay, what is Q naught? Q naught is equivalent nodal forces, and it is special for temperature changes or fabrication error for truss. This is for truss. Okay, for truss. However, for beam analysis, Q naught is for also consider for external loading, where the member get have loaded with member force. The force subjected along the member or on anywhere on the member, so we need to consider the Q naught. But for truss, Q naught is only exists whenever there are effect of temperature or fabrication error. Okay, so I want to show to you how I want to write the stiffness matrix, stiffness equation, or the force displacement equation, which is Q is equal to KD plus Q naught, and for this case there is no Q naught because Q naught is 0. Q naught is 0 because there is pressure of fabrication error considered in this case. So I want to write the equation now. Okay. Okay, so we will have like this. Q is equal to KD, and we focus on 3 value because the unconstrained is 1, 2, 3. K A E times with displacement. For unconstrained, there are unknown displacement D1, D2, D3. Okay, so let's find what is the Q1 value, Q1, Q2, Q3 from the question. Okay, from the question, Q1, okay, Q1. From this, we know that Q1 is negative 150 kilonewton. Q2 200. Q2 is 200 kilonewton. And Q3, there is no Q3. There is no Q3, means Q3 is equal to 0. So it is negative 150, positive 200, and 0. Is negative 150, positive 200, and 0. Okay, for K, so here is all the value. Okay, 0.238. It is 0.238. Then negative 0.054. Negative 0.054. Then 0.281. 0 and 0.25. Okay, if I want to complete this, I may complete this. Negative 0.054, 0. So this is also 0. Okay, now we have established the stiffness equation or the force displacement equation corresponding to unconstrained degree of freedom only because we will analyze this matrix or this equation in order to determine the unknown displacement, because the unknown displacement occur in unconstrained system. Okay, so by having this, I can continue calculating unknown displacement, and since AE, if AE is not given, so we may have the displacement in terms of AE. So D1, D2, D3. Okay, in terms of AE, I will get I will use calculator directly. I use equation with 3 unknown. I will put the value. A1 value is 0.238 for A1. Continue with A1. B1 is negative 0.054. Negative 0.054. C1 is 0. D1 is negative 150. D1 is negative 150. Continue with A2. A2 is negative 0.054. Continue with 0.281. Continue with 0 for C1. And D2 is 200. Okay, continue with A3. A3 is 0. B3 is 0. C3 is 0.25. And D3 is 0. Okay, now I have already get the value. D1 is negative 490.135 over AE. D2 is 617.554 over AE, and there is no value for D3, 0. Okay, so this is the displacement. Okay, so with this displacement value, okay, after calculating displacement, we can actually continue calculate whether we want to calculate the reaction at the support. The reaction at the support is Q4 until Q8. Okay, we can continue to calculate number 1, calculate reaction at the support, which is Q4 until Q8 using a matrix multiplication, or with the displacement as well, we can continue calculate the member forces, or we can also calculate member forces. There are 5 member forces, and the symbol for member forces, because reaction we consider for the structure. Member is element we use small letter, so the member forces we use small letter of Q. So we have 5 elements, so we will determine Q1, Q2, Q3, Q4, Q5. Okay, 5 elements. Okay, using formula. Okay, I want to show how we determine the member forces. One member force is enough. Okay, I want to determine Q4 member forces in element 4. Okay, let's say I want to establish or determine the Q4. It is AE over L. It is negative CX, negative CY, CX, CY. This is the formula. Negative CX, negative CY, CX, CY. Okay, times with displacement. Okay, times with displacement. Okay, for Q4, we must look at the K4 that we have determined in the early stage. Okay, K4. Okay, let's look at K4. Okay, for K4, the label is 1, 2, 7, 8. 1, 2, 7, 8. So for element number 4, so we just have to follow that 1, 2, 7 and 8. So here is 1, 2, 7, 8. D7 and D8 is 0 because of the support. D1 and D2 we have determined here, D1 and D2. Okay, so this is D1, this is D2. So this is the formula. Okay, so it is equal to AE over L. L is 8. Negative CX, negative CY, CX, CY. So we have to replace with all the CX, CY value. CX, CY. 0.866 and 0.5. Negative 0.866 and positive 0.5. CX 0.866, CY negative 0.5. Okay, time with 1 over AE, and it is 490,135. 490,135. 617,554. 617,554. Okay, so AE will be cancelled. AE here will be cancelled. Okay, so we determine the value. It is negative 0.866 times negative 490.135, okay, plus 0.5 times 617.554. Okay, the value, so here is also 0. Okay, so the value we divide by 8, so we get K. So K4 is 91.65 kilonewton. So this is how we determine the member force, okay, for using structure stiffness method. Okay. So basically this is how we analyze truss, the basic truss analysis. The basic truss analysis. Okay, I want to revise back. Okay, this is the truss question. This is the diagram. As you can see here, there are 8 degree of freedom because there are 4 nodes. Okay, there are 3 support, 2 pin and 1 roller produce 5 unknown reaction, and 5 unknown reaction is actually equivalent to the degree of freedom for constraint system. So there are remaining 3, 1, 2 and 3 for unconstrained. Okay, so we put all the information in the diagram. We complete this diagram with coordinate and the arrow. Okay, the arrow is important because without the arrow we cannot identify the near and far end, and due to that we cannot determine the CX and CY value. CX and CY values are important in order to calculate the element stiffness matrices. So please put all this information first before we start doing analysis. Okay, And since this question does not give us the horizontal force, it just give the vertical force and the angle. So using trigonometry, we calculate the vertical force. Okay, so this is the basic mathematics that everybody learn in school. Okay, so we will get x value or horizontal member due to 60 degree. We use tangent 60. It is equal to x is equal to 6.93. So now we already know what is the horizontal length. So we analyze element by element because we are actually we want to analyze the truss using stiffness matrix method. And in order to do that, we have to establish the structure stiffness matrix. And the structure stiffness matrix can only be determined or can only be established by element stiffness matrices. Divide the structure into element first. So we have to analyze element by element, one by one. Since there are four element or 5 elements, this has 5 elements. So we have to establish K1, K2, K3, K4 and K5. Okay, so this is K1. Okay, K2, K3, K4 and K5. And the most important thing is, beside the value is important, because without the right value we cannot get the right the value in the structure stiffness matrix. However, the most important thing is we have to label the element stiffness matrices one by one. Label outside the matrix, the bracket, is the degree of freedom. Okay, the degree of freedom, and the labeling must follow this condition. Okay, that is why the arrow is important. Okay, from the arrow we can determine where is near end, where is far end, where is near end, where is far end. So from let's look at element number 1. Near, for the near end, okay, for the degree of freedom, xy is 5, 6, and for the far end here, near end 5, 6, for the far end 7, 8. So we should label the matrix, the stiffness matrix, okay, according to near xy, far xy, it is 5, 6, 7, 8. 5, 6, 7, 8. If you put wrong label, then you will definitely you will get the wrong answer, the wrong stiffness matrix. Okay, element 2, look at the arrow, okay. So where is near end? Near is C, far is A. So we should label as 5, 6, 1, 2, 5, 6, 1, 2, 5, 6, 1, 2, 5, 6, 1, 2. Okay, 5, 6, 1, 2. Okay, element number 3, we must look at the arrow for element number 3. Look at the arrow, it is 7, 8, 4, 3. 7, 8, 4, 3, because we refer to the arrow. 7, 8, 4, 3. 7, 8, 4, 3. 7, 8, 4, 3. For element number 4, look at the arrow. A is near, D is far. So it is 1, 2, 7, 8. 1, 2, 7, 8. 1, 2, 7, 8. For element number 5, it is 1, 2, 4, 3. X, Y, X, Y. X for near, Y, X, XY for near, and XY for far. So 1, 2, 4, 3. So 1, 2, 4, 3. So with all this label of degree of freedom shows the position inside the structure stiffness matrix. So using that, then only we can determine all the values. So in this matrix, as you can see in this matrix, all this value from value 1, 1, 1, 2, 1, 3, 1, 4, 1, 8 until 8, 8 can be determined from 5 element stiffness matrices. So find one by one. Okay, find one by one. So I don't put all values here because I want to focus on the unconstrained system only, because when I have the unconstrained system value, then I can solve for the unknown displacement. Okay, so you may give this in full if the question asks you establish the structure stiffness matrix. Establish the structure stiffness matrix. Sometimes the question doesn't ask you to establish the structure stiffness matrix. The question just asks you to determine the displacement, the unknown displacement. So in order to determine the unknown displacement, we should know only the unconstrained system. And unconstrained system here, like what you can see on screen, I have put the divider of unconstrained and constrained. So I have already determined all the values 1 1 until 3 3 for unconstrained system. Then using the value, I can solve for the unknown displacement. Okay, I will solve unknown displacement using the stiffness equation or force displacement equation, where Q is nodal forces, K is structure stiffness matrix, D is nodal displacement, and Q naught is equivalent nodal forces. However, in this case, for the basic calculation, the temperature changes and fabrication error not occur. So this Q naught is assumed as 0. So I rewrite only the unconstrained system in order to determine the unknown displacement. And for this one, since AE is not given, so actually we can solve for the unknown displacement, and we get the unknown displacement in terms of AE. In terms of AE, like this, 1 over AE. Okay, and after that we can continue calculating whether we want to calculate the reaction at the support, or we want to calculate the member forces. Okay, both two depend on the unknown displacement. Okay, the unknown reaction, the label is capital Q. Okay, represent the degree of freedom for constrained system. So the label should start from 4, right? 1 2 3 for unconstrained. Constraint start from 4. So Q4 until Q8 is actually the reaction at the support. So we can continue calculating this using matrix multiplication. Means that we have to complete this part lah. We have to complete this part. Okay, this part no need, because the value we time with 0. We can focus only this. Okay, and this is equal, right? Equal to this. Alright, so and after that we can also calculate the member forces. Since there are 5 members, so there are remember member and element is the same. So if element stiffness matrix, we use the small letter for the label, and this is member forces or element forces. Okay, so we use Q small letter of Q to represent the member force. Okay, we cannot use capital here because capital is for the reaction at the support. So Q1, Q2, Q3, Q4, Q5, Q6, and here I have shown to you the example of how we calculate the member forces using formula. So this is all the formula. This is the one formula only. This is the formula AE over L, negative CX, negative CY, CX, CY times with displacement. Okay, there are 4 DOF for element, and we have to use the same label like what we use in K4. Means for near to far 1278 for K4. So here 1278 for displacement D1, D2, D7 and D8. D7 and D8 located at the support, so displacement are 0. So D1 and D2 we have determined. Okay, so when I solve this, I get single value representing the member force for element number 4. Okay, that's all you need to do. When you have question, trust to determine using stiffness matrix. Okay, So I will continue a little bit on the Q knot, means equivalent of the forces considering temperature changes and fabrication error, in the next session. Okay. Before that, you may it may good to you if you redo this and try to solve all the value, all the missing value, or you may check all my value that I have used here. Okay, so for the next session, I will continue with analysis of this truss, considering considering the temperature changes and fabrication error. And after that, I may consider the effect of support settlement. Okay, to complete this truss analysis. After that, the following session after that is for the beam analysis. Okay, that's all for today. Thank you for watching, and Assalamualaikum warahmatullahi wabarakatuh.